Today we're going to talk about the stoichiometry of a particular type of chemical reaction, and that's a combustion reaction. In the past, we've talked about combustion reactions that dealt pretty much with carbon, hydrogen, and oxygen. And if you have just carbon and hydrogen or carbon, hydrogen, and oxygen, you end up with, in a complete combustion reaction, which we're going to assume all of these are, CO2 and H2O, carbon dioxide and water. Now we're going to extend the definition of this to say that if you have other types of fuels than those that just contain carbon, hydrogen, and oxygen, then you're going to form an oxide of every element in that compound. So in this case, we would form not only the CO2 and the H2O because there's carbon and hydrogen in this particular fuel, but we're also going to form an oxide of aluminum. And since aluminum is an always true +3 and oxygen is -2, that's going to end up forming a compound of Al2O3 for that particular reaction. So those are just examples of some combustion reactions. And if it's a more complicated fuel, the problem will virtually always work out or give you information about what the other substance formed will be. Now, if we have an example of this, oxalic acid, it says it's used in the paint, cosmetics, and ceramics industry, and it's found in many plants and vegetables. And it contains only the elements H, C, and O. Now, that's important because the hydrogen, carbon, and oxygen tells us what our fuel, what our original substance is going to contain. This one says hydrogen, carbon, and oxygen. The whole goal of this problem is to figure out what the X, Y, and Z subscripts are. We're going to determine the empirical formula, and we don't know them now, so that's why we're going to put the X, Y, and Z there. Don't forget the oxygen that's involved in the reaction as well. And since all this compound contains is hydrogen, carbon, and oxygen, we're going to realize that the products are going to be CO2 and H2O. Now, our goal in this problem is to find an empirical formula. So let's scroll down here and look down here really quickly. These are the pieces of the puzzle that we need: hydrogen, carbon, and oxygen. And we've got to find a way to figure that out in this problem. Well, look at what it gives us. It tells us that we're starting out with 0.513 grams of our fuel, grams of this oxalic acid unknown, and that when we burn it completely, we end up with 0.501 grams of CO2 and 0.103 grams of H2O. Does it make sense to you that if we can figure out how much carbon is in this 0.510 grams of CO2, that, according to the law of conservation of mass, has got to be the same amount of carbon in this original compound? Likewise, if we can figure out how much hydrogen is in this 0.103 grams of water, we'll know how much hydrogen is in this original compound. Again, law of conservation of mass. Now, we can't do this with oxygen because oxygen is everywhere. It's literally in every compound, every substance that's up here. But we can do it for hydrogen and carbon. So let's do that first. Let's start with our CO2. We've got 0.501 grams of CO2. And we want to figure out how much carbon is in that. We know that the molar mass of CO2 is 44, if we add it up, 44.01 grams of CO2 per mole. And we know that, now we're going to use a slightly different type of ratio this time. Think about it. If we have one CO2, that tells us we have one C and two O's, right? So if we have 12 CO2s, we have 12 carbons. If we have 1,000 CO2s, we have 1,000 carbons. And if we have a mole of CO2, we have a mole of carbons. And that's going to be our ratio. How much carbon is in a carbon dioxide molecule? And now for mass, we need these to be in masses, 12.01 grams of carbon per mole of carbon. We just need the carbon part. And we end up with 0.1367 grams of carbon that we have found. Now think about what we just found. We just found a piece of the puzzle. Now carbon's our second one down here. We don't want to make that mistake of putting it in the wrong place. 0.1367 grams of carbon. Now let's do the same thing with hydrogen. Up in our problem up here, it says that we started out with 0.103 grams of water. And the molar mass of water is 18.02 grams per mole. Now look at what the ratio is going to be for this one. We want moles of water on the bottom, and we need to know about just the hydrogen. So look at our formula for water. If we have 1 mole of water, how many moles of hydrogen would we have? We would have 2 moles of hydrogen for every 1 mole of water because of the formula, okay? So that's what our mole ratio is going to be for hydrogen in water. 2 moles of hydrogen for every 1 mole of water. And now we need the molar mass of hydrogen. Remember, it's just hydrogen, not diatomic hydrogen. This is in the water molecule, the compound, so it's not diatomic. So 1.01 grams of hydrogen per mole of just hydrogen. And we get 0.01155 grams of hydrogen. So we just found another puzzle piece. 0.01155 grams of hydrogen. So now that we know both of these two, think about how we would find the oxygen. Let's look back up at this original problem. We know we've got this much total, and we just found out carbon and hydrogen. So think about it. All we need to do is to subtract those two values from our total up here, and we're going to end up with how much of it must be due to oxygen. So let's do that. We've got 0.513 grams total. We're going to subtract off the 0.1367 grams of carbon and the 0.01155 grams of hydrogen, and we end up with 0.3648 grams of oxygen. So 0.3648 grams of oxygen. Now watch it on your worksheet, guys. On your worksheet, the first several problems only have carbon and hydrogen in them. You do not want to do this subtraction step if you only have carbon and hydrogen. And you will not need this step if you're only dealing with carbon and hydrogen. You would stop here and stop here. So watch for that. I'm showing you a more complex problem in the notes, but don't, if it's easy, let it be easier, okay? So watch for that. Now, if you remember from our empirical formulas problems, we're going to divide all of these by their molar masses so that we can get these in terms of moles. So 1.01 grams per mole for our hydrogen, 12.01 grams per mole for our carbon, and 16.00 grams per mole for our oxygen. When we do, we get 0.01144 moles of hydrogen, 0.01138 moles of carbon, and 0.0228 moles of our oxygen. Now remember, that is not a useful mole ratio, so we're going to divide all of these by the smallest number to get this in the lowest whole number ratio possible. And we end up with 1.0, 1.0, and 2.0. What does that tell us? That tells us that the empirical formula of this problem, or of this particular compound, is, remember, do it in the order that it's given, HCO2. So there's the empirical formula. To get the molecular formula, we're going to need to get a ratio, remember. And that ratio is going to be whatever the molecular mass is, and they have to give us that, no way to find that out otherwise, divided by the empirical mass. And if you look back in the original problem way up at the top, it tells us that the molar mass of the acid, the molecular molar mass, is 90.04 grams per mole. And if we add up 1 hydrogen, 1 carbon, and 2 oxygens, the empirical mass of that empirical formula is 45.02 grams per mole, which tells us that this real compound is twice as big as the empirical formula. So we're going to multiply everything in the empirical formula by 2, and we get a true molecular formula for this compound of H2C2O4. Okay, so there is the molecular formula for oxalic acid. I'm going to do one more problem just to make sure we can pull this all together. We've got compounds that have carbon, hydrogen, and metals that are called organometallic compounds. One of the best known of these is ferrocene, and it's a molecule that contains only iron, carbon, and hydrogen. So the first thing we need to do before we go any further is to make a chemical equation to show what's happening. And remember, we know it's got iron, carbon, and hydrogen, but we don't know the subscripts. And we know that it's going to have a reaction with oxygen when it burns. It's got carbon and hydrogen, so we know it's got CO2 and H2O. The problem with the iron is it's going to form an iron oxide, but iron is in the sea of unknown charge. We don't know what its charge is going to be, except for this nice little statement right here. And look for those, because if it's a question, they're going to give you that information. The iron is converted to Fe2O3. So there's our chemical reaction. And it tells us that we burn 0.652 grams of this substance. And when we do, we get 1.542 grams of CO2 and 0.315 grams of H2O out of this. And it wants to know what the empirical formula is going to be. So remember, our puzzle pieces that we want are going to be and it wants it in the order of carbon, or iron, carbon, and hydrogen. So we need Fe, we need carbon, and we need hydrogen. So it wants it in that order. So starting out the problem, we're going to look at the fact that we've got 1.542 grams of CO2. Do what we did in the previous problem. It's got 44.01 grams per mole of CO2. And remember our ratio, we just want the carbon and the hydrogen out of these compounds. So there's 1 mole of carbon for every 1 mole of CO2 and 12.01 grams of carbon per mole. And we end up with an amount of carbon of 0.4208 grams. So let's fill that in. That's our carbon, 0.4208 grams. We've got one puzzle piece. Now let's get our hydrogen puzzle piece. We know that we've got 0.315 grams of our water. And we know that it's 18.02 grams of water per mole. Don't forget, this is one of the most common mistakes. The amount of hydrogen in water is 2. 2 moles of hydrogen for every 1 mole of water, 1 mole of H2O, and, don't need an equal sign yet, 1.01 grams of hydrogen per mole of hydrogen. And we get a value of 0.03531. grams of hydrogen. So we've got our next puzzle piece, 0.03531 grams. And how do we find iron? By subtracting. We're going to take the 0.652 grams total minus the 0.4208 grams of carbon minus the 0.03531 grams of hydrogen, and we get 0.1959 grams of our ions. We've got our carbon, our hydrogen, and our iron now. So 0.1959 grams of iron. And now for our empirical formula. We're going to divide all of these by their molar masses. So iron is divided by 55.85 grams per mole. Carbon by 12.01 grams per mole. And hydrogen by 1.01 grams per mole. And we get mole values of 0.0350. Well, for iron, it's 0.00, that's a 0, 00351 moles. For carbon, it's 0.0350 moles. And for hydrogen, it's 0.0350 moles. Okay, I'm going to divide these now by the smallest of the numbers, which is 0.00351, and I get 1, 10, and 10. So what does that make my formula for this compound? FeC10H10. And that's stoichiometry by combustion.